Hi, I hope you're able to hear me. Hello, hello, hello. The previous stream ended abruptly. Hope you don't mind that. Please come back, whoever was here. I hope you have received a notification. If you have not, then you have not pressed the bell icon, which is not good. You should have. You definitely should have. That's rude that you are on my channel and you haven't pressed the bell icon. Come on, guys. Do you not want to know when I'm doing this live stream? Do you not want to improve your speed for your edge compute and use ONNX there so that you can improve your overload performance? You do, right? I hope you do. You should. Well, you should care about these things. But okay, so I hope you're able to hear me. I'm just connecting with my phone. My phone is acting up. Yes, it shows that I'm live. And yes, you are able to see me. So join back, whoever was here. Don't lack off. You have to work on this. We have not ended the stream yet. It was an abrupt pause that shouldn't have happened. And we are going to continue. So just before we left off, so there we were looking for the rotation matrix. Now, so this is what it basically looks like. So these are the different axes we want to rotate about. So we only have a 2D image, so we only want 2D rotation, and that would only be about these axes. So we want to rotate our 4 points around the xy axis using this equation, which is cos theta minus sine theta cos theta. So to do this, we was just basically want to multiply it with our transposed rotation matrix, which should be pretty easy actually. So what we want to do is we want to create our rotation matrix. So it will look something like this. So def return rotation matrix, and we'll give in our theta, and I'm pretty sure we are converting it to theta now, so we don't need to worry about that. And okay, so theta would be in what is the dimension for our theta? That's also a thing. So are we printing it? No, we're not printing it anymore. We were printing it before. We don't need to print this anymore. I think we are good now. So we get our row output. We don't even need this print statement. And yeah, okay, print r dot shape. Let's see what it looks like. So r dot shape is 8400 comma 1. So what we want to do is we have our theta. So for all of these 8400 things, or one thing we can do is in our to keep in our final result, let's just not print it here. We know the final result, the fifth dimension, like the, oh wow, the fifth dimension, that sounds so interesting. But yeah, so if we print this, you will see that our shape is 4,5. So 4 are our number of final boxes that we are left with after doing an amends on them, filtering them out based on their confidence scores and some IOU, and 5 is your XYWHR. So that makes sense. So your last dimension, which is -1, is gonna be your thetas. So you'll receive your thetas in somewhat like this. So if I just show you that, so you get all of your dimensions in something like this. So you should get it right like this. So 4,4, and that's not true. That's more like it. So 4, so you get this. You want a rotation matrix for all of this theta, so you can quickly get over with it. So we want to do it in a matrix format so that it is parallel. How can we do that? Now you have these thetas, you want to convert them into rotation matrices. So fuck. So I think rotation matrix would look something like so. Mat is gonna be this for I in theta. So you go through each one of them and you say mat.append, and you append a list where you first pass in your, I think you have to pass in a list of lists. So this is going to represent your so np.cos of theta -1 into np.sine theta, and then finally your, what was the formula again? Sine theta cos theta. So np.sine theta and np.cos theta. So you want to do this for all of your thetas, and not of so thetas, for theta and thetas. and that's how it will go. And finally you will return np.array of mat. So this should make sense, right? This should return you a matrix of shape, print return rotation mat, final res. I don't remember doing any of this. So 4 comma, and you're just getting a single one. This is not correct. What are we doing wrong? We should have received one for each one of them. The theta is 4? How the fuck can that be possible? Are you passing in the fucking shape, you idiot? Yeah, now you're getting it. So, what's the shape of this thing? 4, 2, 2. So, 4 are your batches and 2, 2. So, you want to convert your x1, y1, x2, y2 into this. So, let's say we have our x1, y1, x2, y2. So, let's say whatever. So, let's say we have this 10, 20. So, we have a rectangle here. Let's just create an imaginary rectangle. So 0, 10, 10, 10. Not 10, 10. So 0, 0, 0, 10. 0, 0, 10, 10, 10, 10, 0. So this is your rectangle. And you want to rotate this now. So you do. Oh fuck, can't I just use CV to rotate? Oh fuck, I was just being an idiot. Was I not? Rotate xy points in numpy by some theta. Yeah, this is exactly what we want. Oh, they're using something similar to what we derived earlier. This we can use, right? Okay, this makes sense. Okay, let's go ahead with this one. Thank you, Stack Overflow. We're gonna use you now. So we'll not even import math because we don't do that. We'll just use numpy. Only problem being we will have to do it using a for loop using this function, and I really want to do it using matrices. So how do I do it with matrices? So you have this array, you convert it to degree to radian, t minus ot plus ot dot t. Wow, this is taking way longer than I expected it to take. How did I manage to print these things earlier? Maybe I just print it with for detection. Let's just we keep doing this. But only thing is I really want to see the results for now. So let's just first get xy. So let's ignore the rotation for now. Let's just like we are not gonna rotate the. We're gonna rotate it finally, but I just want to see what the results look like. That's what I'm excited about. Then we'll figure out the rotation logic. It shouldn't be that big of a deal. I think we are just giving it way too much of a time. It should be way faster. And I bet even if I ask ChatGPT to do it, it will do it in minutes for me. But okay, so here we are. We have the final results of shape in the final batches. Final axis of our final result is gonna have our boxes. So just to show it to you. So yeah, so we want to complete this function. So for now, let's say we completely ignore our rotation. So we say our for I in final res. So we go through our box basically, because we just saw that our first dimension is gonna be our number of boxes and the last dimension is gonna be our basically our shape. So if I can show that to you quickly, so let's just say print final res dot shape. I run this thing again just to get our row outputs results, and there you go. Okay, this is giving us an error 4,5, so that makes sense. Now we go here, we say for box and final res, so we are going to our first box, and let's just say our boxes we store here. So our boxes is going to be, and we also want to store their classes. So their classes are, so where you get this, you will also get your classes, which is going to be your sorted classes, and you get only the two keep ones. And here what you wanted to do is let's also store our classes are already in a loop, we don't need to worry about them. And you go inside of a box, you say whatever is your final red, so xywh, you get x1 comma y1 is equal to box 0, which is your x, minus box 3. Let's just do it like this, x comma y comma w. That way it will be much more readable. And then finally you just say x1 y1 is equal to, or you can even say it like, no, I think we'll get to do it like this, shouldn't be a problem. This is just say points, so we'll go like points dot append x minus w by 2 x plus w by 2, and let's also keep converting them to integers right now, because we want the pixel values to plot them as polygons. Then points dot append int y minus h by 2. Not even like this, what the hell am I doing? So you want your x1, why am I being so stupid? So yeah, this is gonna be your first one, where you have your these things. After that you're gonna have, so your x will, you'll go to the next x, but your y will remain the same. After that your third point is gonna be something like where you're in the lower right corner, and then finally you're gonna be in the lower right left corner. So this will give you all of your points. Then you can finally boxes dot append points, and then you can return boxes. And now finally, after doing all of this, we have to still figure out our rotation, but that's just going to be easy. Let's just ignore it for now, because I'm really tempted to plot what our images look like. So let's just say these are our boxes, results, OBB is equal to x, y, w, h, r, and here we pass in our final res. Cool, that would have been a bug later. Luckily we will manage to find this. And then when you have your final res, which is all you need, you can just plot your image, which image.shape is invalid. There's nothing like image. Yeah, that makes sense. So yeah, for plotting the image, we'll have to do some stuff. And then finally transpose it, where you will do something like this. Boom, you have your image. Now what we want to do is, for I in boxes, I hope I have already have Shapely in here. I don't. And we'll have to also, of course. So if you remember from previous line, we were using, why is deactivation taking so long? Here UV, we were using UV for all of this. So you have to just do source.when bin activate. Cool. So you finally have this, and you will just do UV add Shapely in here. That should give you Shapely now. Let's run all of this again. You have your final res, you process them, then you create your polygon. So your polygon is gonna be your I, which is the list of list where you have your xy's, and then you're gonna get your x comma y, which is gonna be polygon dot exterior dot xy. This is pretty standard code that you use to plot a box in your any kind of segmentation box or your rectangles or anything using matplotlib. So when you finally run this, linear ranging inputs operand 0 does not have enough dimensions, has 1. Func operation requires 2. Why would that happen? Let's print I. Oh, we are going through boxes. No. We have to go through result. Yeah, naming issue. I don't know why I'm facing a lot of them. Oh wow, what the fuck happened here? That's fucking funny. We have it in some 4,000 or something like that. Oh, we didn't. Yeah, I get it. So we didn't change the offset that we applied to them. So what we'll have to do is, just like here that we applied the offset of the various classes, we'll have to do that. We have to create the offset classes where we do np.concatenate similar shit and do the offset classes equal to, let's name it final classes to avoid any confusion. So final classes all and np.new access. So this will add another dimension to it. After that we go to our de-offset classes. So we're doing pretty much the same thing we did during when we were offsetting them, but now we are just gonna subtract it from there. So we do offset classes comma np.zeros 8400. So I shouldn't have hard coded it like this. So for now let's do it like len of, or just final res dot shape 0, and here you will need, here it will remain 4 because we are still gonna do it for our first axis. And yeah, and image dot shape 2, that will also remain the same. I hope you're not rechanging your image. Cool. So you concatenate them, and then finally you do is final res minus equal to the offset classes. Or you could just, no, you'll have to do it like this, right? What happened now? Cannot interpret 4 as a data type. Where did that happen? Cannot interpret 4 as a data type. Okay, you need another, you need it as a tuple. Sure, let's do it. All the input arrays must be of the same dimension, but along axis 0, the array of 2400 and the array at 1 has size 4. Why is that happening now? Final res should also have the same shape, no? Oh, why am I doing it for offset classes? I have to do it for D offset classes. Oh, that's fine. That makes sense. Nope, still not getting it. What's happening now? Oh, somehow it didn't do that. Let's just print out what our D offset classes look like right now. We are doing some weird bug. The boxes are correct. Oh, it's all 0, 0, 0. Why is that? Our final classes are all 0 is what you're saying. How did you sort the classes again? That's correct. Boxes plus offset classes is also correct. Interesting. So you're not able to get the when you're sorting your classes like this, you've somehow lost that information. Well, let me just print my final classes to make sure that's the issue I have. Because I think if that's the case, then the simplest fix would be just to look at the amount of offset everything requires, so divided by 640, and that way we should be able to receive what is the class of everyone. So instead of getting our classes like this, I think when we are doing soft NMS compute, somehow it has arranged them differently. It has changed the order of things, so that's why we are getting this error. So boxes might have changed their order inside of the thing, and that's why we are instructed to keep only the first 4 of them. So instead of doing it like this, what we can do is we have our final class. So to calculate our final classes, we'll just do final res. So let's do it in a loop just to avoid any confusion. For I in final res, and we have to only look at x because we offsetted it along x only. So if you can see, so np.concatenate offset classes np.zeros into image.size, and our offset classes is of 1 dimension. So all of 4 we ignore, but the first one is our goal. So here we go on the first one, and we say that let's go to final classes, and they say final classes dot append I divide by image dot shape 2. So let's just print our final classes now. We should be able to receive our results. Okay, some another bug. That's fine. But that's not correct. List indices must be integer or string, not tuple. Where is it happening? Okay. So what's happening is, yeah, got it. So final classes, we are not able to, oh, why am I going into zeros? And that will be why, right? There I'll not get my classes. Here I'm getting my classes. So yeah, 5, 5, 13, 5. That's why we are getting these so far away. So we do this, and at the same time we want to calculate their, how do I convert them back? I think just taking the mode will fix it, right? So final res, so I in range len final res this. Simpler way would have been just to do it like this. So final range final res dot shape 0. So we go through all of our final results, and what we do is we final res I comma 0, we divide by this, and at the same time we also, where did it go? We also update our final res to be mod equal to, this should fix it. Oh, again the final classes thing is causing a issue, so we just want to do np.array of this. This should fix it. Not like this. Okay. Okay. So we'll have to do it later basically. And finally, before doing anything else, And are we getting it now? Oh, we're just getting it in minus. That's fucked. That shouldn't be happening. Why are we getting a negative value? Return rotation mat, we don't need it right now. Oh, we are still subtracting it, that's why. We don't need this, thank you. And boom! You're getting your results. That's correct. Right. That looks fine. Only these two objects are a bit fucked for some reason. Can it be because of rotation? Or can be that the model sucks itself, so soft NMS was not able to fix it very properly. But there shouldn't be that much difference in between soft NMS and NMS, so I'm not sure what's causing this. So this is all correct. So somehow for these classes we fucked up. I think class wise we are doing really good. And also, did we start the training? I don't think so. We were uploading it on Drive, right? So I think it has been uploaded. We can open up our collab and start training the different model. But yeah, for now, focusing on what we were doing here. So we haven't written the rotation code yet. It can be that after rotation it fixes itself. Let's just ask ChatGPT to do it. I have 4 points. This should be it. ChatGPT should manage this simple problem for us. We don't want to worry ourselves too much with the code and stuff, and I also want some decent optimum code that doesn't take too much time as such. So rotate points, it is using this, and it is again going through a for loop. I didn't want to go through a for loop as such. Okay, whatever, we'll go through this approach only then. So yeah, while doing this itself, let's do it like right here then. So you have your 4 points. When you are adding them, before that only you will do your, okay, so for each point you want to do it. Now you have R with you, so I think the simplest way to achieve this will be to giving X and Y. So let's just say, let's define another function, rotate point, and we need to rotate a single point at a time, so we don't need to worry about that, as it is anyway going to be using it like this. So, and we have already converted it to theta degrees, so we don't need to worry about that. What does it expect in theta? In radians. So we'll have to worry about that. Theta is equal to np dot pi and into theta divided by 180. Let's go. And np dot sine theta, and then you just say rotated x new, y new, x into cos t minus y into sine t, x into sine t plus y into cos t. And I think, yeah, matrix multiplication shouldn't be that difficult now. Okay, so what we want to do it, at every point we want to do these operations on this, and we'll get our x new, y new. So what we actually want to do is, if we just get our rotation matrix, which is pretty easy. So your rotation matrix is something like, you're passing in your result, right? So you are getting your R every time. So your rotation matrix will look something like cos t, sine t, I will define these here. So let's just and there you go. And this is gonna be R. So there you go, and your rotation matrix is gonna be cos t sine t, comma sine t, and this is gonna be negative. Let's just delete this for now. And what you want to do is you want to multiply this so that you receive your points xy in a way that's rotated like this. So what you really want is you got these points and what, so new boxes, rotated boxes somehow should be equal to, so you have your 4 points inside of it, right? So 2 to 2 in each one of them. So in each 4 you have 2, so 4 comma 2 is your dimension here. And for that, so your boxes look something like this. Let me just open JS Paint again. That way it's easier to visualize these metric operations. So you have something like this. Consider it your rows. So this is your x1 y1, your x2 y2, x3 y3, x4 y4. This is what you have inside of your points thing. So before adding them to boxes, all you need to do is multiply them with this matrix so that so this is a matrix looking something like this right now, minus sine t, so and sine t comma cos t, and you want to multiply them with each other so that, so this is 4 into, so these are 4 rows and 2 columns, and this is 2 rows 2 columns. So if you take a dot product of them, you should get these two, and it is a row column multiplication. So your each row will multiply with this, which you don't want. You want your row to multiply with this. And okay, so this is where it gets tricky, right? So you want your x new to be this thing, the result of this summation, and your y new to be the result of this summation. So okay, so for row column you just need to take a transpose of this. So if you take a transpose of this, this will become minus sine t, and this will become plus sine t, and then you will have your first row multiplying with this. So this will give you x new, which should be equal to x into cos t minus y into sine t, which is exactly what you are doing here, minus y into sine t, and finally you will get x sine t plus cos t. I don't know why we're getting confused with this earlier. This is pretty straightforward. Yeah, that's why I wanted to let it go and first see the plot and then figure this out. So at the same time we also figured out that we have to de-offset the images to finally get them in the correct shape. So yeah, that's great. We were able to work on something else while we managed to figure this matrix multiplication out. So yeah, this is pretty straightforward now. So you want, before doing this with your points, you want to just multiply them np dot dot dot, and not even dot product actually. This is your matrix multiplication. So you will do np dot array points into, so this is your symbol for matrix multiplication in numpy, and you matrix multiply them with your rotation matrix dot transpose np dot array. This should be it. And you did something wrong. Now we have them all the way over here, which shouldn't be the case. Why would that happen? So are we doing de-offsetting the results before or after? We're doing it before, right? Where is the de-offsetting thing? Yeah, so we are doing it before, so there is no issues there. but somehow we are getting them all the way over here, which shouldn't be the case. What are we doing wrong now? Let's see. So I think theta fix these boxes. This is 100%. These will fit on that. The only issue being they are not on the right place, and this also fits correctly now. I think that's the kind of fit we were achieving previously as well. Yeah. So that is correct. The only thing is we need to relocate them all the way over here, which somehow has been fucked. Oh, I think I know why that happened. So we did it on points, but the points, so it is rotating them by origin, but instead it should be rotating them by their own center, right? So for their own center, instead of rotating them before, what we should do is, okay, so we should manage to rotate them before. How can we do that? So your rotation matrix should not be this straightforward. You need to first rotate them at their own center, which is your XY. You need to rotate your W and H based on that. And then you need to do your things. Wow, it's again, it's getting tricky again. And I shouldn't get so tricky. But okay. So it's simple actually, and not that big of a deal. What we want to do is, from the box's perspective, we want to calculate the rotation based on the center of the box instead of calculating the rotation from this origin. So right now it is calculating the origin from this origin 0, 0, which shouldn't be the case. So to fix that, what we need to do is, I think for these things the theta should be so small that they didn't get affected at all. The theta was slightly higher for them, and that's why their x got completely misplaced. To fix this, we have these 4 points. Before rotating them, we subtract x comma y from them, right? So we subtract x comma y, which is a single, which should be a single row, because I want to multiply, I want them to broadcast in a way that each row gets xy subtracted from it. Then we do this rotation, and finally once we have the rotation, we add our np.array x comma y. And boom, there you go. Perfect results, everybody. Perfect results. Come on, guys. Need to say something about this. So we are finally getting our results the same way we are getting here. And let's just quickly check out if they match in terms of their, so yeah, so finally we have this code working. ChatGPT didn't really, I think this really helped us. We saw this formula before, but somehow we were not able to figure out this exact calculation from it by then. But after working on the first ignoring rotation part, and then calculating our x1, y1, x2, y2, and then finally after that we were able to figure out how to add the rotation part into them, and we are getting the same predictions as we are from our Ultralytics model. But come on, we can't just visually see and say that okay, they are the same predictions, cool, we are good to go, we can go home now. We have to even see the mathematical results. So let's just quickly check out what each of our polygon looks like. So print polygon. So let's see. So these are our x1, y1s, and we need to match them with our x1, y1s here. And where do I get them? And we can even match them by xywhr directly, which should be pretty easy. So let's just say results.obb, which I've already printed, I think, and there are my xywhrs or my xys. I can match with anything for that instance, but it is converting back to 1024, which I have not done right now. I'm plotting them on the converted image. So what we should do ideally is, instead of plotting them like this, we should have had something like, so let's do it by n. So we are getting the normalized results now. So for each point before getting it, we are going to be dividing it by, so finally we can do it actually. So we'll just divide the whole thing, the whole array, that is decode another set of brackets, that's so shit. So you're gonna divide the whole thing by np.array of your image.shape2 image.shape3. So by doing this, we should be able to divide it by our x and y. So xywn, this should give us the normalized results now. And what we can do is, our image would be cv2.imread, the same image that we were reading before. And this should be the image that we are plotting. And we don't even need this quiz and statements anymore. It should be able to plot it itself. And then when we are getting the results from our OBB, we will not be directly passing it inside of our polygon, but first we will be multiplying it by our np.array image.shape0 image.shape1, and lo and behold, and if we run this, not right now, we have not fixed this yet, and there you go, beautiful results with 1024 by 1024. So now we can print our polygons right here, and you should be able to see everything. And by the way, since we are writing all of this at the same time, we can have both of them ready, because we are gonna have to write all of this anyway. So only thing that has changed is this thing. Let's just remove this line. Man, we are able to do it with a one-liner. That was cool. Always feels happy when we are able to do it with a single liner. So these are our results. Let's copy them and see how close they are. So for oriented bounding box model, so this is our first step that we took in this process, and we were able to, let's compare results. So first of all, we have our results from our ONNX. I'm just gonna copy this. ONNX results. And Control Shift V. That should be much more readable. And then we have our Ultralytics results. Let's just see what they look like. For XY, right? Right, guys? You're aware of it now? Good. So they look pretty much the same to me. If we have any difference, then we'll have to see what is causing that difference. That would be pretty interesting to evaluate. So yeah, these are our results. So let's take an example. So it's okay. So they are in a pretty different format. So here I think we have XY. Well, like the X1, Y1 is this point, X1, Y2, then something like that. So let's just see what it looks like. So let's just compare it with anyone. So let's say 923.4008. Do we have something like that? 923.4008. So we have two cases with 923.4, which is matching. And let's see what the other points look like. So with 923, we have 241. we have 240.7. When we round them, they will read to the same result. 1 pixel difference there. And then 798 comma 64, 798, yeah, these will lead to the same result pretty much. 223. Okay, so we have 1 pixel here and there in most of the images, but it works. This 1 pixel difference can also be there because of the soft NMS that we are doing, and this shouldn't worry us that much. I think it is matching really well. I think let's just say one more. So 920.17, 920.14, and 9.44, 8.77. Yeah, it's really close. So we are able to get the same results from ONNX as we were able to get from YOLO. And this is what we wanted to do in this video. Next video, we'll be benchmarking the performance and also do it for detection model. So once we have done the oriented bounding box, the detection should be really simple, as the only thing you need to do is send the rotation matrix as 0 by yourself. You can use the same pipeline. Just when we were sending this rotation here as a row matrix -1, instead of doing that, your rotation would be 0 for each of the cases, and you should pretty much get the same results from the soft NMS, because soft, yeah, like it will be doing the same thing just for rotation is equal to 0. And I think the results are actually really amazing, because this is what we wanted to do. So we are able to get the same results from our oriented bounding box using ONNX-Runtime as we were able to get from the Ultralytics pipeline. So yeah, you can see for yourself. Let's compare another point for that instance. So 683. So do we have anyone with 683? Yeah, there you go. 683.2, 683.4. Then you have it with 247. Here you have it with 248. I think we should be able to figure out this 1 pixel difference as well. I remember it being really close. It can also be the case that the model is not very well trained right now, the model that we pick up, and that's why the results that we are getting are not as amazing as we expect them to be, because the soft NMX might be getting heavily sensitive, like the NMS methods might be getting very sensitive to the model training, because the model might be predicting very shitty results with more confidence score. So that all makes sense. So I also wanted to show you guys how you basically train a YOLO model. So let me just open a new collab notebook for the same. I have already uploaded the dataset as we did at the start of the video. If you have been watching from the start, which happened in another video because somehow my internet decided to fuck me up in the middle of the stream, I might edit these videos out so that it is easier for you guys to follow along. I think sometimes it takes me too much time in some of the things I do, and that can get confusing for you. So yeah, we'll do that from next video. Right now I'll just quickly show you how to run inference, how to basically train your model from scratch using YOLO. So I'm gonna do, first of all, pip install Ultralytics. That's what you have to do. Lytics, you will connect. It's really simple actually. It will not even take me much time. Let me just quickly do it for you guys. So pip install Ultralytics. You import your YOLO model. You can import your, if you want to see your results, that is, but I think basically training should be fine for now. You just need to import your YOLO for training. It's that simple actually. That's how simple the YOLO people have made the training part for you. You import your YOLO, and you also want to, so basically we want to mount our drives. I always forget how to mount your drive on Google Drive. I'll just quickly see how you can do it. Yep, there you go. From Google Colab for Drive. From one more thing that we have done wrong here is that from Ultralytics import YOLO. We should quickly get something to asking us that you show you want to connect your drive, and we'll say yes. There you go. This is my ID. Continue. Now my drive will be connected here. So what I can do is, you're just gonna love how simple this is gonna be, I'm sure. So you go on my drive, you go on the .v1 dataset that we have, you go to your YAML file, you just need to change your path basically, because when we first created it, we put in our path for our, wait a minute, did we not edit this? I guess I must have forgotten to. So let me just quickly go here. So yeah, .html file. So you want to copy this, paste it over here. So these are all your class names that you want to store here. Your part to your test train images. We don't need this this kind of comment right now. We want to change our path to basically our collab path because right now it has my system path in it. So we convert that. We have our train set, our validation test, our test set. Cool. And that's all you need. Yeah, so that's all you need for your YAML file. So you go here, you say YAML path is gonna be, what was the YAML path? And just copy path. Cool. That's it. And then you want to do model is equal to YOLO, and you put in your favorite YOLO version. For oriented bounding box, I have always been a fan of YOLO 810. I don't know why. I think it works better than YOLO V11 in most of the cases that I have seen. So you do that, and then finally all you want to do is model.train. It should show me the type hints. No, not like that. Show me the type hints. Not even type hints, basically just hints, I guess. Or we can just, yeah, we'll just open up the Ultralytics docs. Not even this. We just want to open, not even dataset. We just oriented bounding box. How do you train this? Model to train, you give in your YAML path, epochs, and image size. So you just go here, you do this. Results is equal to model to train. You give in your YAML path. You have your epochs, which is 100 for now, which should be enough. And your image size, I'm going to keep it to 640. I don't want it to take too much time while training. And there you go. Your training has basically started. It will download some fonts and shit to display it cleanly. If you are running it on your laptop, you can also view the results in TensorBoard if you have it installed. And it will just start training your model. It's actually that simple. I'm not sure why it is downloading YOLO 11. I have particularly asked it to use YOLO V8 OBB. Just give me a second. I'm pretty sure it must be using YOLO V8 and OBB. Okay, it has downloaded 11 though. What is that? Model is equal to YOLO V8 OBB. Okay, just some. Maybe it's just downloading it because it's the newest model or something. They have hard coded it or something. I'm not sure. So yeah, that's it. So it is right now. So Collab has to load the images from your drive, which takes a bit of a time because it has to basically import your dataset from your drive to your Collab and load it into your RAM. So this is a bit of a slower process where it will be loading each of the images into your uh, instance RAM of your Collab notebook. But once it is finished, you will just have to go through all of these. It will just go through all of these images. It will show you the results for your classification laws, box laws, DFL laws, which is very common in detection task and stuff. All of these things you'll instantly able to see this, go through your training. It will also store the results inside of runs if you are able to see. So inside of runs you will get all of your results stored in with whatever model you train. I think once I ran it and cancelled it and ran again, so that's why there is a train 2. So this is where your latest results are going to be. All of your training arguments are going to be stored here, so you can also use this to look at what all arguments you can pass in while training so that you can train a model that is more customized for your needs. And you will have your weights here. It will also automatically be going through your validation dataset and check which is your best model according to your validation datasets so that you can pick up the best one while training. So yeah, I will say it's a pretty clean pipeline when it comes to training, and most of you people must be already aware of it. The tricky part comes when you want to boost the inference speed, and here we have accomplished the first step towards that journey. So I hope you found it cool. Let me just quickly upload this code on GitHub. I guess it would be helpful for you guys. uh, to start working with this kind of a pre-processing and stuff, so you can experiment with your different models, convert them into ONNX. I showed in the previous video how there is a command in YOLO itself. So there is this command, CLI command known as YOLO export, which you can use to convert any YOLO PT model to your ONNX model. This is some kind of a failure, I'm not sure what that is, but yeah, so it works in most of the cases as I showed you in the previous video. And yeah, you just import your model like this in here, whatever part to your model is. You start your session, you give in your image like this. So whatever standard, you just have to do cv2.read. And here I think I have used image loader to load the image. So yeah, you can use this whole code basically. Once we are done with the detection and segmentation code as well, we would be creating a API ourselves, similar to the way YOLO has it. So you can load up any model you want and it will go through the pre-processing, post-processing steps for you. And that should make it super simple for you to use ONNX as your runtime in any of the scenarios. um, so yeah, other than that, you have to provide your number of classes that would be specific to your data set. Then you just load your model, you start your session, you pass in your image, and then you collect your classifications, class scores for each class. You calculate your confidence score for each of the instances, which would be the maximum of your class score for that particular sample. Then you sort based on the confidence in scores, because when you're passing it to the NMS model, you want to sort the results before, as NMS would pick up the best like the most confident box and keep merging it until it finds it is able to combine based on the IOU threshold that you have given, that we also explained in the previous video. But here we are not using the NMS that completely discard the second image. Instead, it gives it a score based on this formula that they introduced in soft NMS, which basically is inversely proportional to your IOU. So you can go through the soft NMS paper to understand more about it. Then after doing that, we converted our rotation. So these are particularly what all we collected from our output. So we calculated our rotation, we calculated our XYWH, we calculate our classes, we offsetted the classes so that we don't have inter-class intersection, which might be true and you might need it. Once we have it, we calculate whatever boxes we want to keep. We what all boxes we have to keep in our data set of our final data set. We got those boxes. Then we finally de-offsetted those boxes by taking their modulus, and also we calculated their class from those de-offset itself. So basically how much of a de-offset we did to it based on the image size, we will be able to get which class it belongs to. So that is pretty neat. And yeah, so for 0, so yeah, this will be pretty straightforward. You will get your classes directly, and then we finally wrote this code which converts your XYWHR images into your XYXYN. We stumbled upon it a little bit, but we finally able to get the rotation part working. We got a bit of confused previously, but then we were able to do it as a matrix operation itself, which should be optimal in the long run, as numpy should manage to parallelize that instead of running it in a for loop. Uh, when we were working on the optimization step of our timeline, which is for the speed boost, at that time we might think of changing this as well, to remove this for loop as well and to be able to parallelize it using a matrix multiplication itself. But yeah, that is about to come. Our next step would be to get our pre-processing working for segmentation and detection tasks, and then finally we can start working on the refactoring code to create the API. And after we are done with that, then we'll start working on the further speed boost part of things, where we try to optimize the uh, preprocessor and post-processor that we are writing to basically work with this uh, ONNX-Runtime library. And yeah, one more thing that I wanted to show you guys is how less of a memory are we taking right now. So let's just quickly see what all do we have in our Py project dependencies. We have Shapely, IPyKernel, Matplotlib, and all of this. Let's reveal it in Finder. and let's get an info on this. So we are using 447.8 MBs for all of these libraries when we are using ONNX runtime. Now let me quickly show you how much memory we consume when we use Ultralytics. So for Ultralytics, we in dependencies we have IPy Oh, this is not Ultralytics, is it? Okay, okay. So we don't have matplotlib here. To have a fair comparison, I'll have to install matplotlib and OpenCV Python as well. Or I think it should be already there. Let me just quickly check. So what we can do is pip show. Hi Fawaz, how are you doing? You have asked that does it provide the flexibility like Ultralytics YOLO? So what flexibility are you talking about? Are you talking in terms of training or are you talking in terms of inference? And if you're talking about inference, what exact flexibility do you need? We are currently working on it, so we might be able to add the specific functions that you want to add. That's what we are trying to do here. In terms of use cases development. So yeah, so if you go through Ultralytics, which is, let me just show you the Ultralytics documents. So for training, I'm still recommending you to use Ultralytics as the API is, I mean, amazingly simple. I am also running this, so you can see how in such less lines of code I'm able to start a training process, and I can also go through the arguments and modify the hyperparameters for training as flexibly as I want to, as Fawaz is just highlighting how amazing Ultralytics is. But for inference, when it comes to inference, so as you can see, there are only detection, segmentation, pose estimation I have not looked at right now, classification and oriented bounding box. So I've taken up these three tasks for now, which is detection, segmentation and oriented bounding box, and I'm trying to write inference preprocessor and post processor similar to Ultralytics, but that uses ONNX-Runtime and NumPy only. So you should be able to like in terms of inference, I don't think there is much things you need to do unless you're like the confidence, like majorly when you're doing inference with Ultralytics, you are changing your confidence threshold, your IOU threshold that we are providing, and these are one of the most of the common tasks that you want to do with Ultralytics, which is your detection, segmentation and classification, oriented bounding box detection. So we will be able to cover all of these cases. Okay. uh I will definitely let you know, but for that I'll have to know where to contact you. Yeah, so yeah, as I was just saying that you can run inference on these cases, so that should be fine. I'm not sure what else you will need in terms of flexibility. We'll also be providing all of these things that provides convenience when you're working with Ultralytics, so yeah, that you can get your output in a cleaner format. And yeah, so result wise, as I just showed you, this must not be very helpful, but as you can see from Ultralytics, the result that we have got our preprocessor to be pretty much the same. So when we are running inference with Ultralytics, we are getting these results. Shit. My Insta handle should be in the channel's about page. Have I not added it? Oh, okay, it's not there. So Insta handle. And let me just attach it on the chat itself. Give me a second. So, or you can also connect to me on LinkedIn. I think LinkedIn will make more sense. Instagram is better that way. Give me a second. So there you go. That's my LinkedIn handle. You can contact me there and we can discuss whatever you want to discuss after the stream. So I've just completed my bachelor's in mechanical engineering this year itself, and I'm currently working as an AI engineer. So yeah, so these are the results we are getting from Ultralytics, and these are the results we are now getting from our ONNX pipelines. So pretty good, right? It's almost the same, only so we were analyzing them and we were at max getting 1.5 pixel difference, which is kind of cool. And we are running our training here. So yeah, I think I've mostly summarized whatever we have done in the stream. And yeah, I was just telling you that we should make a repo out of this so that you guys can also see it and maybe send me some merge requests and shit. I love that. We might make this better so that so let me just create a new repository. YOLO ONNX. What do we call it? Framework library. And so on. This library, this code base aims to provide a standard library to run inference using ONNX-Runtime, various YOLO models, including detection, oriented bounding boxes, segmentation, and achieve the same results as the topics. I think that's too big of a description. Let's just give it for various YOLO models. And we'll copy it there. So we'll add it in the README itself. So let's not add a README here. Let's create this repository. And so this is our YOLO and experiment. We'll add git init, git add. Okay, we already have a README. I'll just add it here. This post. How do you make checkboxes in Markdown? So yeah, so tasks. So first of all, we have let's just have it as a title itself. So what was our first task? So pre/post processing. That's how you make it, right? So here you have detection, oriented bounding boxes, and your segmentation. So this we have done finally. Other than that, you have your task. So I'm just writing my timeline in this markdown to make it easier for us to follow up. So yeah, so that's what we have done till now. TensorRT. Oh, TensorRT, okay. Yeah, TensorRT, you can, ONNX can directly run on TensorRT, right? Only the numpy instructions you'll have to see if you can send to TensorRT. TensorRT is, okay, no, I'm getting it incorrectly. TensorRT is a SDK, yeah. Okay, that's different. Yeah. So you can run ONNX on TensorRT, is it? Is that the case? Oh, okay, makes sense. Yeah. Yeah, once you have your pipeline ready with ONNX, then you can run it on pretty much anything. I think, yeah, what I was confusing it with was ONNX has this thing where you can use DirectML and stuff for AMD also, right? So I thought you were talking about that. But yeah, that would be pretty fast. Also, I think DirectML, also this deep sparse, yes. Deep sparse is also something very similar, right? Where it tries to, so it is also a inference engine which tries to speed up things. So here you go. So this is uint 8. This, I don't trust this too much as you will be losing on some mean average precision here. But yeah, if accuracy is a major thing for you, it still provides a decent speed up when compared to Pytorch and ONNX-Runtime. So that is also something you can look at. Yeah, definitely. I'll make sure to ping you for us. Cool. Um, yeah, so let me just add this to my GitHub so that you guys can access the code. I'm not sure if it would be very visible in these 2-3 screens we have open here. If you have a bigger screen, then it might be benefiting you guys. I have my MacBook Air, which is only 13 inches, and these many screens in here makes it a bit difficult to display all the code correctly. But yeah, so these are all of our pipelines added to the GitHub README. Oh, I'm just gonna make my first commit. Code work badly formatted, but working code for uh, OBB detection model. Ah, shit, we didn't add. Remote add origin. Let's just copy this line. That should be it. Okay, YOLO ONNX experiment it is. Ah shit, I should have added things to get ignored. Ah, now it will have all the stupid details that were not necessary. Okay, I'll have to make another commit right now, guys. I can't bear this. That's stupidity. Let's just go here and quickly, yeah, let's just have a git ignore in here. And here we'll add our .when. Is it not added to? Yeah. Datasets runs. You can also have in git ignore. .8.yaml we can have in git ignore, and we are in the experimental, right? Yeah. So .8.yaml we can have in git ignore. Other than that, hello.py, why the fuck do we even have this anymore? Yep, and that's all. Yeah, that's all the git ignore things we need. So let's clear it out. Git add dot. Added git ignore for unnecessary things. What happened? Ah, shit. 3m's in the commit. Yeah. So cool. And also PyCache. Ah, dude. Why so many bullshit commits? Can I just delete them? I need them. No, just delete them, but I need them. Whatever, man. I'm being stupid now. Missed PyCache. Be added to git ignore. Cool, guys. Also, don't forget to feed my alter ego and add some stars to this whenever you use this. Cool, so this is all that we have done till now. I want to delete this. Can I delete them from Git itself? Will that work? Delete file. This file was deleted. Commit changes. Yeah, we can just delete them from here only, right? Because I don't want them. Yeah. That's how you have to do once you have done a mistake. Commit changes. I don't want all of these unnecessary files showing up here. And .ds store, why do we need that? So one more thing for git ignore, .ds underscore store. We'll add it just for our safety. And finally, you have all the files that you actually need. Cool. Wow, that was awfully long to just add a git ignore. But yeah, there you go. So we have oriented bounding box done. We have to do detection, we have to do segmentation, and these are our next steps. Cool, guys. I think that's all for this video. I just thought of one more thing. Let's have it like this. Wow. If I can just type. Yes. And that should be all. So I'll just add one more time. So many comments already. Yeah, let's go. Yeah, so what's the problem with all of this merge branch main? Yeah, so this is correct, right? So I merged them, and now I should be able to. So these are my new commits, right? And my that thing, git ignore, I added restore. So yeah, so git add dot. So are they committed already? What happened? Shit, I need to get better with git. Few changes in readme and updated git ignore. Ds. There you have it, guys. Finally, that was awkwardly long. But yeah, I hope the project made sense to you. I'll leave you here now. And I guess I'll just edit these videos for you because it might be annoying to follow me on live stream sometimes. I understand that. And so, yeah, sucks to suck, but no, I know. I'll make it easier for you guys, don't worry. But yeah, look at the big picture. And the big picture is you have these results now. And we are able to run your ONNX inference, which should allow us for faster inference. But yeah, one more thing that we were looking at, we completely missed that. So we saw that we have 447 MB of memory being used on our ONNX thing. Now let's see how much memory we are consuming on our Ultralytics thing. So let's see how much memory does Ultralytics takes. So here you go. Let's get the info. And 942, so almost double. So we are able to save half of our memory footprint just by using ONNX, even though we are still using Shapely and stuff. And I don't think we had even imported Shapely on our YOLO ONNX right now. Have we? Oh, we have. Okay. Then only, yeah, we are able to save half of our memory just by converting it to ONNX, which is good. Yeah, I think there's nothing more, right? Nothing extra here. Yep. It must be importing OpenCV. It's a dependency for it, so that's why I'm not worried about that. Cool. That was all, guys. Hope you had fun. The end was pretty much enjoying, but I know most of you have skipped already because I cannot see anyone here. So yeah, see you in another video. We are done with the first part of our video where we had to write the oriented bounding box detection code, and I've pushed it to GitHub. Go check that out. Add a star to that repo to feed my alter ego. That's all. See you. Bye bye.